Good morning. All right, so we're going to finish up 1.2 today and then get into 1.3 also. Again, I'm going to have to push the homework back a little bit more because we're definitely not going to get through 1.4 today. So that won't be due probably until the middle of next week at this point, but continue to work on it through the weekend, what we've covered at least. Send me questions as you have them. We will finish up 1.3 and 1.4 next week, and then the homework will be due as soon as we finish that up. Okay. I think that's about all in terms of announcements for today. Any questions, comments, concerns before we get started? All right, and as always, if you think of anything, just let me know. But let's jump back in here. Example 13, section 1.2. So the first thing we want to do here, and all we're actually going to do on these, is convert these into rational exponents, right? So we're going to rewrite each of these radicals as a rational exponent, a fractional exponent, because in a lot of cases, that's going to help us to actually simplify these things down, right? In cases where we might not otherwise be able to simplify. All right, so let's take a look at the first one here. We've got 1 over the cube root of x to the 4th power. So if I wanted to rewrite this using a fractional exponent, what could I do first? Think about what we did yesterday. We have those radicals. All right, good, right? So we know that cube root of x to the 4th in the denominator. We can rewrite that with 4 in the numerator, 3 in the denominator of our exponent. So I'm going to write this as 1 over. All right, give me 1 second. Yeah, so 1 over x to the, in this case, it's going to be 4/3, right? Because the 4 would go up top, 3 would go on the bottom. Now, another thing we could do with this one, because we have that x to the 4/3 in the denominator now, what's another way we could write that if we wanted to? Good, right? So we could rewrite this now as x to the negative 4/3. And that's all we're doing with these right now, right? And the reason, again, for this is because if we can get it into a form like that, a lot of times that'll allow us to operate with these exponents in a much easier fashion than we could actually operate with the radicals that we started with, okay? Any questions on rewriting that one now? All right, so let's take a look at the second one. So we've got 2 square root of x times 3 times the cube root of x. It's the same thing. We want to rewrite these as rational exponents first, and then we'll see what we can simplify from there. Okay, so what's one thing we could do here? Okay, so we start with that first set of parentheses. I have my 2. How could I rewrite the square root of x? Good, right? So that's going to become x to the 1/2 power. Because again, in this case, that would be a 1, and this would be an understood 2 as your square root, so we would get 1/2. All right. So then what could we do with the second set of parentheses here? Good, right? So we keep our 3, and then that cube root of x is going to become an x to the 1/3 power. Because again, we understand that exponent is a 1. We have our 3 as our index, so we can put 1/3. Right, now that we've done that, now we can actually combine these two things where we couldn't have done it in radical form. So if I want to combine these now, what am I going to have to do? Good. So we're going to add the exponents, which means we need a common denominator. So if I find the common denominator between 1/2 and 1/3, what's that going to give us? 6. Good. So if I change 1/2 to something over 6, what is 1/2 going to be? Good. It's going to be 3/6 for the first one here. And then we're going to have 3 times x to the 2/6 for the second one. And then, like we said, we're going to add those exponents together because we're multiplying, right? And whenever you multiply like bases, we add their exponents. So if I multiply all this together now, what should we end up with? Good. 2 times 3 is 6. Add your exponents. 3/6 plus 2/6 is going to give us 5/6. And that's all we're going to do, right? We're just going to work it up to that point. But again, notice here, there's no way to combine a square root of x and a cube root of x unless we first convert them into fractional exponents. Okay, so that's why this is useful. Any questions on that one now? All right, so now the third one, we've got the square root of x times the square root of x. Now notice that x and the square root of x are both inside the bigger square root here. So what do you think the first thing is that we might want to do? Good, right? So inside the square root now, we can change that square root to an x to the 1/2. I'm going to keep the bigger square root for now, but inside here, I'm going to have x times x to the 1/2 power. All right, now that we've done that, what can we do? Good, right? So we have an x times an x to the 1/2. So how am I going to combine those? Good. Add the exponents. So in this case, that would be like x to the 2/2 plus, and then it's an x to the 1/2, right? So we're going to have an 3/2 power. And again, if you want to see the work for that, right, we have x to the first times x to the 1/2. Common denominator is 2, so that gives us x to the 2/2 times x to the 1/2. And that's how I got the x to the 3/2 power there. Okay. Now, what else could we do here? Good, right? So we have the big square root around the whole thing now. We can also change that to a fractional exponent. So what's that exponent going to be now? We're going to have x to the 3/2 inside, and then we're going to have it raised to the 1/2 power on the outside. Good. All right, and then it looks like Matthew's got the final answer there. So now when we raise a power to a power, we're going to actually multiply those exponents together. And so overall, this should end up being x to the 3/4 power, and that's our final answer. Okay. So whenever you have one like this and they ask you to rewrite it as rational exponents or fractional exponents, just make sure get rid of all of your radicals, get everything down to just a fractional exponent. Any questions on that one now? Oh, sorry. Let me go back. All right. So are we just looking at the last one there, Christina, or just overall the process? Overall. Okay. So in general, whenever you see a radical and you're asked to rewrite as rational exponents, we want to take whatever the exponent is, that's going to become the numerator of our fraction. And whatever the index is, that's going to become the denominator. So in other words, if I have something like square root of x cubed, or let's say the 4th root of that, right? This right here is my index, so it becomes the denominator of my fractional exponent. And this number right here, the exponent, becomes the numerator of my fractional exponent. So then I'm just going to rewrite this now as x to the 3/4 power. And then if we have some where there's multiple radicals or there's multiple things to work with, then you're just going to convert each of them. And then we just have to make sure we go back to all of our rules or laws for exponents. So remember, when you're multiplying, we add exponents. If you're dividing, you would subtract exponents. If you're raising a power to a power, then we multiply those exponents together. Right? So those are all the things we have to remember in addition to just changing these over to rational exponents. Does that answer your question? Okay. Any other questions there? All right. Now, rationalizing denominators. Okay, so it's going to be useful in a lot of cases to eliminate radicals that are in our denominators. So what we're going to do in that case is we're going to multiply numerator and denominator of our fraction by an appropriate expression, right? A lot of times it's just going to be whatever we have in the denominator, but you'll see some cases where that's not what we actually do. But that's going to be what we call standard form once we do that. Now, this is one thing that we do a lot in 171. You'll see it in 172 if you take that, because in trig we get a lot of radicals in our denominators and we want to get rid of those. And then once you get beyond that point, a lot of times I tell students, okay, it's fine just to leave radicals in the denominator. But if you're ever asked to rationalize your answers, right, that's what that means, is get rid of any radicals that happen to be in the denominator. All right, so we want to take a look at these. So we got 2 over square root of 3. And we're going to try to put it in standard form by rationalizing the denominator. All right, so does anybody remember how we would rationalize that denominator, get rid of the square root of 3 in the denominator of that fraction? We're going to multiply top and bottom. You could change it to 3 to the 1/2 power, right? If you want to do it that way, that would work. But really, we're just going to multiply top and bottom here by the square root of 3. And so now let's think about what that's going to give us, right? Because square root of 3 over square root of 3 is 1, right? We haven't changed the value of the fraction by doing this. If I multiply straight across now, though, what are we going to end up with? Good. So we get a 2 times the square root of 3 in the numerator. And then our denominator now, square root of 3 times square root of 3, is just going to give us 3, right? And another way to think about that is if you do the square root of 3 times the square root of 3, we would multiply those two numbers together, keep them inside the square root. That gives us square root of 9. Now the square root of 9 just becomes 3. But the shortcut there is just to say, oh yeah, they're both the same. Those square roots are going to cancel each other out, and therefore we just get a 3 in the denominator now. And that's all there is to that process, right? So whenever you're asked to rationalize, that's what we're going to do. Now, that's because it's a square root. We're just going to have to do that. You're going to see on the next two problems, we might have to do something a little different to get rid of the radical in the denominator. But for square roots, that's all we're going to do now. Any questions on that one? All right, let's look at the second one. So what do you think we might want to do on the second one here if we're trying to rationalize or get rid of that radical in the denominator? Okay. So we could, right, rewrite it as 5 to the negative 1/3, right, by moving it up and making it a negative exponent. That's still not technically considered rationalized because 1/3 still represents a radical, and then the negative would move it to the denominator. So just changing it to a fractional exponent is not going to rationalize it for us, okay? Now, the other thing is you could change it to 5 to the 1/3, but that's still not going to necessarily get rid of what we want to, right? Because that 5 to the 1/3 still represents a radical. So let's think about what we did on the first one here and see how that process could apply to this one. So what could we multiply top and bottom by here if we're trying to rationalize? All right, so let's multiply by the cube root of 5, right? So let's start there. I'm going to multiply numerator and denominator by the cube root of 5. Now, if I were to do that, what's that going to give us? Okay. So we're going to get a cube root of 5 in the numerator. I'm going to keep it like that. Now, be careful in the denominator, right? If I multiply the cube root of 5 times the cube root of 5, we're basically doing this now, cube root of 5 times the cube root of 5, what would that end up giving us? Yeah, it's like 5 to the 2/3 power, right? Because we're multiplying a 5 to the 1/3 and a 5 to the 1/3. We could add those together. Or you could say this is the same thing as the cube root of 25, right? Because 5 times 5 would be 25, and then we keep our cube root. Can we take the cube root of 25? Is 25 a perfect cube? It's not, right? So we can't simplify that. So this is still just the cube root of 25 in my denominator now, which is not rationalized, right? I still have a radical in the denominator. So I've got to go one more step now to end up with something that I can actually take the cube root of. So what do you think we might want to do at this point? Exactly. Multiply by another cube root of 5. Okay, so I'm going to multiply top and bottom by the cube root of 5 again. Okay. Now the numerators, when I multiply those, cube root of 5 times cube root of 5, that's going to give us the cube root of 25. And then what are we going to get in the denominator? Now we're going to get 5 in the denominator, because what we really end up with is cube root of 25 times the cube root of 5. That would be the cube root of what? 125. And what is the cube of 125? 5. Okay. So in this case, because it was a cube root to begin with, we actually had to multiply by that cube root of 5 twice to end up getting rid of the cube root. Okay, so with a square root, we just have to multiply it once, and those square roots cancel out. With a cube root now, we need 3 of them, right? So we have the one that we started with, and then 2 more that we multiplied by. That's how we're going to rationalize in that case. Any questions on that one now? All right, now let's look at this last one. Okay, so that's right. So we're just multiplying it multiple times, right, to end up getting rid of a cube root. So with a cube root, you would have to multiply it by itself 2 more times. If it was a 4th root, you would need 4 total, so you do it 3 times. 5th root, you'd have to do 4 more times, right? So it's basically whatever that index is, you're just going to need that many of them to get rid of that radical. Okay. So if we look at this last one now, what do you think we're going to have to do? All right. So again, you could rewrite it as 1 over a squared to the 1/7 power, right? That's a possibility. But again, our goal here is to get rid of whatever radical we have in the denominator. So what I want you to notice here is we have a fraction. It's all under this 7th root. So this is really like the 7th root of 1 over the 7th root of a squared. That's why we're asked to rationalize it, because we have a radical in the denominator. So if I want to get rid of that radical that's in the denominator now, what do you think we're going to have to do? Okay, so if we multiply by just a squared, right? So just like the previous ones, we can multiply by what we have in the denominator, right? So the first one we multiply by square root of 3, the next one we multiply by cube root of 5. This one we could multiply by the 7th root of a squared, right? So if we were to do that, we have the 7th root of a squared. We'd have to do the same thing in the numerator, right? 7th root of a squared. Now, here's what I want you to think about. Is that going to be enough to get rid of the 7th root for us? It's not, right? So we're going to have to do it again. Or is there something we could do differently here so that we could just multiply that one time and end up getting rid of the 7th root? Is there something we could change that to so that we could just multiply by a single fraction and get rid of the 7th root up front? Okay, so almost. If we do a to the 7th, right, let me switch these. So let's say this was a to the 7th instead. Well, the 7th root of a to the 7th there, those are going to go away, but then we've still got the 7th root of a squared that we started with, right? So we don't want to multiply by the 7th root of a to the 7th. We would want to multiply by the 7th root of a to what power? Think about the fact that we're combining it with that 7th root of a squared that we started with. Almost, right? So you're thinking on the right track, but we don't want to get a -7 in there. We actually want to get a +7 in there instead. Okay, closer, right? Because if I do 6, How many a's are we going to have in there if we do that? And we started with a squared, and then we're multiplying by a to the sixth. How many a's would that be total? Okay, right. We need an a to the fifth, right? Because if we want to multiply by something to end up with 7 total a's inside the radical now, a to the fifth would do that for us. Because now in the denominator, that a squared times a to the fifth is going to give us an a to the seventh, and then we can take the seventh root of that. Okay, so that's kind of a shortcut so that you're not just constantly multiplying by the seventh root of a squared until you get to something you can take the seventh root of. Just say, okay, I know I've already got a squared. I need 5 more a's in there to give me an a to the seventh, and then I can take the seventh root of that. Okay. Now, if we multiply these numerators together, what's that going to give us? What's the seventh root of 1? Just 1, right? And so then we just keep the radical that we've got there. So this is seventh root of a to the fifth. And now, like we said, our denominator here is just going to give us the seventh root of a to the seventh power. We're multiplying seventh root of a squared times seventh root of a to the fifth. That's going to give us the seventh root of a to the seventh. And what is the seventh root of a to the seventh going to be? Just a. Good. Right, so in our denominator now, we're just going to have a. And again, that's not to say that you couldn't just multiply by the seventh root of a squared over and over and over again 7 times, right? Or 6 more times, I guess, compared to the one that you started with, to end up with the seventh root of a to the 14th power, and then you could actually take the seventh root of that. But in this case, it's much easier just to say, okay, I've already got a squared. I need an a to the fifth to give me an a to the seventh, and then I can take the seventh root of that. Right? It saves us a whole bunch of steps in there. Any questions on that one now? All right. Now we're going to move on to 1.3, algebraic expressions. All right. So in general, right, algebraic expressions, the most common one we're going to look at are what we call polynomials. Okay. So a polynomial with a variable of x is going to be some expression that can be written in this form. Now, that form looks really bad, right? Okay. So let's just break it down. Think about what each of these things actually represents, because really polynomials aren't as bad as what that looks like. In general, these a sub n's are all just going to represent numbers, okay? And so those are going to be real numbers. And in this case, the n value in the exponent is going to be some non-negative integer, okay? So we can only have integers there, no fractions, and they all have to be positive or 0. Now, when we talk about the degree of a polynomial, it's always going to be whatever that highest exponent is, okay? So whatever we have as our highest exponent, that's what we call the degree of the polynomial. And then each of those things that's separated by addition or subtraction is what we call a term of the polynomial. Right? So we would have a term a sub n x to the n, then a separate term would be a sub n minus 1 x to the n minus 1, and so on. But notice here the exponents just keep decreasing by 1 until you get down to a term that has no variable at all. And each of these first things here just represents a real number, which are coefficients of that polynomial. We're going to look at actual examples of polynomials with real numbers in there. So I think it'll make a little more sense, hopefully, once we get to that. But in general, if you can write something in that form, then we call it a polynomial. So here's some examples of polynomials. So 2x squared minus 3x plus 4, that's what we would call a trinomial, right? Because in this case, tri means 3. And so we have 3 terms, the 2x squared, the negative 3x, and the positive 4 are each of the 3 terms for that one. And then again, when we look at degree, we look at that highest exponent. So that 2 right there is what gives us the degree of that polynomial. The next one here is what we call a binomial, bi meaning 2. Okay, and so we have 2 terms, the x to the 8th and the 5x. And in this case, the degree is going to be 8 because, again, we look at our highest exponent on our variable, and that's how we get the degree of that polynomial. Right, now, once we go beyond 3 terms, we typically just number the number of terms, right? We don't actually have a name for that. So we would just say this is a 4-term polynomial. Those 4 terms are the negative x to the third, negative 1/2 x to the third, x squared, negative x, and 3. And the degree of this one is 3 because, again, the highest exponent on our variable, even though it's at the end this time, okay, is 3. And then there's some more examples here. Another binomial, 5x and 1 are the 2 terms. In this case, the understood exponent is a 1. Okay, and so that's how we get the degree of 1 for that one. If we only have a single term, we call that a monomial. Mono meaning 1. Okay, so 9x to the 5th is our only term, and the degree of this one is 5 because that's our highest exponent. Right? And it is possible also to just have a number, right? And we would still call that a monomial because 6 technically has a degree of 0 because there is no variable on that term, right? So if there is no variable, then we would just say the degree of that monomial is 0. Any questions on any of the terminology here or how we know the degree or the number of terms or anything like that? All right. So now let's look at addition and subtraction. Okay, so we want to find the sum of these 2 polynomials. So in general, when we're adding and subtracting polynomials, we can only combine what we call like terms. And what we mean by that is they have to have the same variables, they have to have the same exponents. Those are the only things we can combine using addition and subtraction. So if I look at these 2 polynomials that I'm adding together here, what would be 2 like terms that I could actually add together? Good. So we have an x cubed in this one, and we also have an x cubed in this one. So if I add x cubed plus x cubed, what is that going to give us? Okay. So be careful, right? It is going to be 2x cubed because when we're adding now, we have to make sure we have the same variable, same exponent. That's what makes them like terms. And then we're just going to add their coefficients. Well, the coefficient of this one is a 1. Coefficient of this one is a 1. 1 plus 1 gives us 2. So we're going to have 2x cubed. So make sure, remember, the only time we're going to add exponents is when we're multiplying. In this case, we're just adding like terms. So we're just adding the coefficients together, and we're going to keep the x to the 3rd power. Any questions on that one? Just that part? All right, let's look for other like terms. What else can we combine here? All right, the x squared terms. Good. So I have this term here. Notice I'm going to box in the entire negative 6x squared, and then I'm adding that to a positive 5x squared. So if we add those together now, what's that going to give us? Okay, good. We're going to have a negative 1x squared or just negative x squared. So negative 6 plus 5 is negative 1. Keep the x squared. That's a negative 1x squared. Any questions on combining those terms? Okay. Do we have any other terms we can combine? Good. We have a positive 2x and a negative 7x. So if I combine this positive 2x and this negative 7x down here, what's that going to give us? Negative 5x. Perfect. We're going to have negative 5x or just minus 5x. And is there anything else we have here? Yeah, we still have the 4. There are no like terms to combine the 4 with, so I just have to make sure I bring that down. So it's a positive 4, so I'm just going to bring down the plus 4, and that right there would be our sum for those two polynomials. Any questions on any of those steps for that one? All right, so now we got the same two polynomials down here at the bottom, but this time we're finding the difference, we're subtracting. So if I start subtracting like terms, same thing, I want to find my like terms. I have my x cubed and my x cubed. What am I going to get when I'm subtracting this time then? What's x cubed minus x cubed? It would be 0, right? Okay, because if I subtract something from itself, right, they're going to cancel each other out, and so that term just goes away. So this x cubed minus x cubed becomes a 0. Those terms cancel. All right. Now we're going to look at our x squared terms. So again, I have my negative 6x squared here, and then I'm subtracting 5x squared. So if I do negative 6x squared minus 5x squared, what does that give us? Good. A negative 11x squared. All right, then we're going to look at our x terms. Again, we have our 2x here. We have a negative 7x down here. So if I do 2x minus a negative 7x, what are we going to get? Good. So remember in this case, if you want to kind of write it out to the side, 2x minus a negative 7x, when you subtract the negative, that becomes addition. So we really have 2x plus 7x, and that's going to give us a 9x. So this becomes positive 9x. And then what else do we have to have here? The 4, right? So just bring down the 4. It's still a positive 4, right? So that's just going to be a plus 4. And that would be our answer this time. Any questions on the subtraction there? All right. So now we're going to multiply. So we got 2x plus 1 times 3x minus 5. And notice here at the top, they tell us we're going to be using FOIL to do this. All right, so remind me, what does FOIL stand for? Good, right? So we have our first terms, and we're going to do our outer terms, then we're going to do our inner terms, and then finally we'll do our last terms. Okay, so first outer inner last, or first outside inside last, however you want to say that. So if we do our first terms this time, what are we going to multiply together? Good. The 2x gets multiplied by the 3x. What is 2x times 3x? 6x squared. Good. So 2 times 3 is 6. X times x should give us x squared. All right, then we're going to go to our outer terms. What are the outer terms? Good. 2x. And make sure in this case, right, it is a -5 that we're multiplying by, right? So if we multiply a 2x and a -5, what should we get? -10x. Good. 6x squared. We have our minus 10x now. Then we're going to go to our inside or inner terms. And so what are those terms going to be? Good. The 1 and the 3x. And if we multiply those together, what should we get? Positive 3x. That's a plus 3x now. And then finally, our last terms, that's the only two things left. That's going to be the 1 and the -5. And so what is 1 times -5? -5. And then we always just make sure we combine any like terms that we have. So if I combine like terms here, what's that going to give us? Good. The -10x plus the 3x is the -7x. We have 6x squared minus 7x minus 5. And that is our final answer. And again, just to reiterate, FOIL is just an example of distributive property, right? I'm taking the 2x and distributing it to both of my terms in the other set, taking the 1 and distributing it to both terms in the other set, and then I'm combining like terms. So whenever you're thinking about FOIL, just think it's basically just distributive property. The reason I say that is because we will have some things that have like 3 terms and 3 terms. We just have to make sure that we're distributing everything to everything else. Any questions on that one now? All right. So here we go. So now we've got another product, but this time we've got a binomial times a trinomial, right? So 2 terms times 3 terms. All right. So does anybody have any clever ways of multiplying these together to make sure that we multiply everything we're supposed to? All right. So when you say take out a term, are you saying factor out a term? I want to make sure I'm clear on what you mean by take out a term. Okay, because in this case, there are no common factors, right? So there's nothing I can really factor out. So yeah, the x squared in this case, we really can't do anything with. We're not working backwards yet, right? So make sure it's clear, right? We're actually multiplying these together. We're not factoring. So don't worry about the factoring piece of this, right? Because you could technically factor it further than it is now. Okay. All right. So multiply all the terms of the trinomial by the terms of the binomial. That's exactly what we're doing, right? So we're taking each of the 2 terms from the binomial and we're distributing them to each of the 3 terms in the trinomial. Now, one thing that I think is helpful and for some people, and if this doesn't work for you, that's fine. If you just want to distribute, that works too. I'm going to use a box here just to make sure that I hit every single term that I'm supposed to. And so when I say that, what I mean is I'm going to create a rectangle. In my rectangle now, I need 2 terms for my first one, so I'm going to split this rectangle in half this way. And then I need 3 terms for my other one, so I'm going to create 3 boxes this way. So then along the left-hand side here, I'm going to put my 2 terms for my binomial, so that's going to be the 2x and the positive 3. And then across the top of my box, I'm going to put my 3 terms for my trinomial. We have an x squared, we have a negative 5x, and we have a positive 4. Again, this is just an organizational chart to make sure that we multiply all the things that we're supposed to multiply. All right, so now we're just going to multiply and fill in each of our boxes here. So my first step is to multiply the 2x and the x squared. So what would 2x times x squared give us? Good. Our 2, and then x to the 3rd power. Okay, then I'm going to continue to the right. I'm going to take the 2x, and I'm going to multiply it by the negative 5x. So what's 2x times negative 5x? Good. Negative 10x squared. Then we're going to go to the 2x and the positive 4. What's 2x times 4? Good. Positive 8x. Now I'm going to move to my second row. I'm going to take the 3, multiply it by the x squared. So what's 3 times x squared? 3x squared. Good. Then we're going to do 3 times negative 5x, which would give us what? Negative 15x. All right. And then 3 times 4 is positive 12. Good. Okay. So again, that's just a way to make sure that the 2x gets distributed to everything and the positive 3 gets distributed to everything. If you can do it without the box, that's perfectly fine, right? Now we got to combine like terms. Okay, so we got to look here. 2x cubed, there are no other x cubed terms, so I'm just going to bring down my 2x cubed. Okay, now I'm going to look for my x squared terms. Well, I have a negative 10x squared and I have a positive 3x squared. I can combine those. What's that going to give us if we combine those? Good. Negative 7x squared. So we have a minus 7x squared. Okay, now I'm going to look at my x terms. I have my 8x and my negative 15x. So what do we get when we combine those? Negative 7x. Good. And then finally, I have that 12. There's no other constants to combine that with, so I'm just going to put positive 12 or plus 12. And this right here is my final answer now. But again, all this is just taking the 2x, distributing it to each of my terms in my second set, taking the 3, distributing it to each of the terms in my second set, and then combining like terms. That's all we've done. The box is just an organizational way to make sure that we've multiplied everything we're supposed to. Any questions on that one now? All right. Now, special product formulas, okay? Oh, let's stop there, right? Because I'm not going to have time to get through this whole thing. So we'll stop there. We'll pick up next week with the rest of this section. And like I said, we'll get into 1.4 next week also. Continue to work on the 1.1 to 1.4 homework. I will push it back into next week, though. But continue to send me questions on that throughout the weekend. I'll be checking email and everything. Let me know if you've got questions. But have a great weekend, and I will see you all on Monday.